Hello. In my left hand, I'm holding a splendid device from the early part of the 20th century. It's a device for providing excellent illumination. And if I now point the lamp to you, I hope you'll be able to see a splendidly luminous flame burning there. And also you can see the green diamond shape there, the green precious stones of some kind, emerald light. And this, of course, is in fact an early type of bicycle lamp. Cyclists used to put this onto their front of their bicycle and cycle down the road. And as you could see, it provided a wonderful source of illumination. So how did this come about and how was it invented? Well, the flame which is burning in there, which you can see quite clearly, is actually caused by a gas which is burning. The gas is generated from inside this container at the bottom down there, inside the lamp there, and the gas is called acetylene. Today, I'm going to talk quite a little bit about acetylene and its chemistry, and also its importance, how it was discovered, and hopefully this will put you a little bit more into the picture to appreciate this splendid gas, which is still a major industrial chemical today. So we'll put down our lamp now very carefully, and I shall extinguish the flame by turning the knob at the top. What this is a fine jet. It's what we call a tapered needle, and it extinguishes the flame by removing the supply of water. As I said, later I will come to explain the details of this when we start on our experiments with acetylene. So, what is acetylene? Acetylene is a hydrocarbon. It's made up of carbon and hydrogen only, and it's a particularly simple hydrocarbon. It's got only 2 carbon atoms and 2 hydrogen atoms. Its formula, therefore, is C2H2. However, there are 2 other hydrocarbons which contain 2 carbon atoms, and these are called ethane, formula C2H6, and ethene, or ethylene as it used to be known, formula C2H4. Now, in order that you can appreciate a little bit more about these substances, these 3 hydrocarbons, all of which contain 2 carbon atoms, I have prepared a little table to show you. And in this table, you can see not only the names of these hydrocarbons, but a little bit about how they are made up and the description of the shapes of the molecules. So, as I've said, the molecular formula ethane, C2H6, an unsaturated hydrocarbon with single carbon-carbon bonds, relatively unreactive. Then we have ethene, C2H4, unsaturated hydrocarbon with a carbon-carbon double bond and very reactive. And then we have at the end today's gas, which is ethane, popularly known though as acetylene, C2H2, which has a triple carbon-carbon bond and which is also very reactive. So those are the details, some very simple information about 3 types of hydrocarbon, all of which contain 2 carbon atoms. And now I have some models to show you. The models, they illustrate a little bit more about the shapes of these molecules. So this here is ethane, C2H6. You notice the bond between the 2 carbon atoms which are black, that's what we call a sigma bond. It's a very strong bond. And you'll see that the 3 carbons here are tetrahedrally orientated around the carbon atom. So the bond angle's 109.5 degrees, which is the tetrahedral angle. However, ethene is a planar molecule, and there you see the 2 carbons there, and you have 4 carbon atoms here. And in between we have the sigma bond, which is here, and then we have the 4 carbons there. Now, the pink and the violet, these represent the electron clouds. They're called pi electrons, basically, and they form the very reactive. They enable ethene to be very reactive because it's a relatively high electron density. So those are on either side, as you see, of the central carbon-carbon bond there. And finally, we come to our topic for today, and this is acetylene or ethane. Now, this model here represents the most important part of this model is actually the fact that the molecule is a linear molecule, and we say that the carbon-hydrogen carbon bonds are the carbon-carbon hydrogen bonds 180 degrees. It's a straight line. And we have, once again, the strong sigma bond between two carbon-carbons in the middle, but as you see, two sets of delocalized electrons, the pi electrons as we call them, drawn in pink and in violet. Now, this model, although it shows the electron clouds, doesn't actually represent exactly the shape of the molecule. And I have for that purpose a diagram here, and what it shows you is that actually the two sets of pi orbitals, they actually form a cylinder, a cylindrical sheath around the two carbon atoms. And they naturally constitute an area of very high electron density, and that, of course, contributes to the great reactivity of acetylene. So having shown you then a little bit about the molecules, the structure, I'm now going to turn on to some experiments. So we'll put our models away to one side. We can put them back here. And now onto the actual preparation and properties of acetylene gas in the laboratory. Now, the way in which we make acetylene in the laboratory today is from calcium carbide. Calcium carbide, CaC2. It's a very unusual compound because it's a compound which calcium ion has a charge of 2+, and the carbide ion is C2, 2-. Now, the first carbide that was actually made synthetically was made by Edmund Davy. He was a cousin in 1836. He was a cousin of the great, very famous chemist Humphrey Davy, and he was attempting to make potassium, which had relatively recently been discovered by Humphrey Davy in 1809. In 1836, Edmund Davy was attempting to make potassium not by electrolysis, as had been done by his cousin, but by reducing potassium carbonate with carbon. He was roasting. Carbon was a good reducing agent, had been used since antiquity for extracting metals, and Edmund Davy was roasted potassium carbonate with carbon. But what he got was not what he expected. He got a substance which had a pale grey colour, which when reacted with water gave off a gas which he identified as something quite different. He called it carburet of hydrogen. He also noticed that this gas burnt with an extraordinarily luminous flame, which I will shortly demonstrate. Now, he noted the gas, which today we call acetylene. Acetylene was actually fully investigated by the French chemist Marcelin Berthelot in 1860, and he was the man who gave it the name acetylene. We shall now therefore prepare some acetylene from calcium carbide and water. The reaction is, I have already in my flask here, I've already put in some calcium carbide. The tap funnel here contains water, and I'm going to collect the gas over water by downward displacement of water in a pneumatic trough. Now, to do this, I'm going to kneel down because I have to control the water flow onto the calcium carbide very carefully. If I allow too much water to run in, then the reaction will be over in a few seconds. So, if you don't mind, I'm going to very carefully open the tap, and as water hits the carbide, you will immediately see a lot of frothing and bubbling. There it is. And there, as you can see, bubbles will start coming out. There we are. We have a steady flow now. Let's have a steady flow. We have a steady flow of water now on calcium carbide, which is reacting very vigorously indeed. And you can see bubbles here. Now, those bubbles initially are bubbles of air, because the acetylene is displacing air from the flask, so we allow a few of these bubbles now to escape. However, we judging that we've got rid of most of the air, so we now start collecting in our beautiful glass trough here. This is called pneumatic. This is a way of a pneumatic glass trough, it was known. This method was first invented by the English chemist Stephen Hales in 1722 and subsequently brought to great world usage by the great English chemist Joseph Priestley in the 1770s. So you see we're now almost full, and our acetylene, of course, which is not soluble in water, so I've got a jar full here. I'm now going to collect more acetylene into a second jar. So we're now bubbling the gas through. You see it's coming here, and some of it's escaping around the side. That's a little concern. And very shortly, I may add a few more drops of water. So there it is. It's continuing to bubble away. And I'm going to do some tests, obviously, that's why I'm preparing the gas. So I'm just going to slide another cover slip onto the gas jar here, and then we shall collect another jar of acetylene. However, this third jar will be slightly different. So this jar is now full of acetylene here, and now we fill this with water like this, and we stand it over our trough like that. So that's called a beehive shelf, that white thing there. Now notice, this time I've only collected a tiny amount. You saw there wasn't much acetylene in there, it was mainly full of water. But when the water drained out, it was replaced by air. So what we've got in here is a mixture. In this jar here, we have a mixture of air and acetylene, about 10 to 15% acetylene, and the majority of it is air. And there's a very good reason for doing this. So, what I wanted to do first of all is to illustrate for you the flammability of acetylene gas by placing a lighted split to the mouth of the jar. Now, for that purpose, I will put on my goggles here, and you'll see an extraordinarily yellow, smoky flame. And the reason for this, let's do this very carefully, we'll hold it up, there is no hurry. What I'm going to do is to remove the cover slip and then apply the flame. And there you see a beautiful flame, very, very smoky, of acetylene burning in air. And there it is, you see, plenty of smoke has been produced. Now, why is this flame so smoky? Well, first of all, there is a very high proportion of carbon in the molecule of acetylene. In fact, 92% by mass is carbon and 8% is hydrogen. So in the air which is around it, there is simply not enough oxygen to enable full combustion to take place, which is why we had this considerable amount of smokiness. Now, before we move on, actually let's move on now to this jar here, which only had 10% acetylene. And this jar here is I'm going to now ignite this, and I shall not be holding this in my hand as I ignite it, because the combustion will be much, much more rapid. And hopefully you will see a very, very luminous flame indeed. And there you see a whistling sound and the luminous flame which went down to the bottom of the jar, no smoke at all. Now this tells us that this combustion was a complete combustion. There is no carbon left behind. The products of that reaction were merely carbon dioxide and water vapor, which was condensed on the side of the jar there. Now for the third jar, for the third experiment with our third jar of acetylene here, I wanted to show you its reaction with bromine. Now, bromine is an intensely toxic liquid. In fact, at room temperature and pressure, it's a liquid, but it's a gas and it has a dark color, and it is particularly suitable for testing the reactivity of unsaturated compounds because it takes part in what's known as an electrophilic addition, and the bromine is decolorized. Now, you may know that ethene, C2H4, very readily decolorizes bromine water. However, with acetylene, which one would expect, logically speaking, a double bond, a triple bond should be more reactive than a double bond, you would expect the reaction to proceed even more rapidly, which is what I thought before I started these experiments. Please watch carefully. Here I have bromine water. This is a solution, a very, very dilute solution of bromine in water. And at this concentration, it really doesn't health hazards. It's very, very dilute indeed. More concentrated solutions are extremely dangerous. Toxic vapor, bromine, unbelievably toxic and corrosive, so we stay well away. But at this concentration, there is no great danger. So I am now going to pour a small quantity of bromine water into my acetylene here. I'll do it over here. Hopefully I will be able to do this without allowing too much bromine to escape. I'm going to open this. As I said, there is this is very dilute, and I'm pouring in that much there. Now, what I'm going to do now is to shake this up very vigorously, hoping to show you that the bromine is decolorized by this extremely reactive gas. And now as I shake it, we're hoping to see the yellow color, which is already very faint, to see it disappear. But as you see, no matter how much shaking I do, there is some fading of the color, but we'll all agree that the fading is very slight indeed. I mean, that's not exactly an exciting reaction. There hasn't been a great color change. Now, why does this happen? Well, the reason why this happens is because the carbon-carbon bond, the triple bond in bromine, is unbelievably strong. It's a much stronger bond than it is in ethene, which is the double bond. And because it's so strong, that bond is far less likely to be polarized by the presence of the bromine. As I said, this takes this as an electrophilic reaction, electrophilic addition. It's much less likely to be polarized because it's such a powerful link between those two carbon atoms. And although there is just a hint, a little bit of decolorization, that really is all we're getting at the moment. However, if this reaction were to be left overnight for a few days, undoubtedly this will be decolorized. But in today's experiment, the purpose of this really is to show sometimes in chemistry there are more factors involved in the reactivity of a bond than its multiplicity. So now what we're going to do, I'm going to allow this water to flow into here, into our flask, and in so doing, I am displacing any remaining acetylene which is present, but that's not the main object of this procedure. At the moment, the reason why I'm doing is because it does make sense to look to see what's left behind. We must always examine all the products of every chemical reaction. So what I have prepared here is some filter paper in a funnel, and I'm going to now take the solution which I have made from the reaction of calcium carbide with water, and any reasonable person, reasonable knowledge of chemistry should allow us to deduce what the products are. So acetylene was one product, and the other product will investigate it first of all. So I'm going to turn off the water supply there. We now have a reasonable amount of our solution from the reaction between, and we can now pour this back into here. This is just water. And now we have a reasonable amount of solution here, and we can pour this solution. And you see it's gone quite milky, by the way. And we're filtering off the solid now. We're filtering off the solid. We can hold this up so that you can see it quite clearly. And of course, as we filter it, so the solution which comes through, which obviously contains calcium, because the calcium must be left behind, there is a colorless solution. Now what we can do, we can find out something about the nature of this solution by adding some universal indicator dissolved in water. Now you see this has an added universal indicator added to it. There it is. I've got my little bottle of their universal indicator there. That is water. It goes green. It's neutral, pH of 7. And what I'm now going to do is to remove my funnel here, so we can carry on dripping there. And now if we add universal indicator to our solution, you will notice a dramatic color change. And there you see it's gone purple. And the reason why it's gone purple, obviously, the solution is strongly alkaline. And the reason is because in this reaction between calcium carbide and water, not only is the product acetylene or ethyne, which is incidentally a very interesting reaction because from an inorganic compound we have prepared a most important organic material composed of carbon and hydrogen only, C2H2. And in this situation, what gets left behind is calcium hydroxide, CaOH twice, otherwise known as lime water, what I have in here. And that is demonstrated by the fact that the universal indicator has turned purple. Now, acetylene undergoes several other reactions, of which perhaps one of the most spectacular is its reactions with copper chloride solution or with silver nitrate solution. It forms a most unusual type of a compound, which is unbelievably unstable and therefore very dangerous, and which detonates violently because of that, because of its instability. So I'm going to show you, we have prepared earlier a small sample of silver acetylide. Now, what we've got in here, I've got the apparatus that we did this. This takes a little while, by the way, which is why we prepared it in advance. The way it was prepared was by bubbling acetylene through a 0.05 molar solution of silver nitrate in a boiling tube and then filtering the product. So there we have the filtered product, and in there you should be able to see a dark brown solid, and that solid is silver acetylide. Now, this is moist, and the whole thing is as I'm showing here. The interesting formula, by the way, for silver acetylide, which I would never have guessed, it's Ag2C2. An alternative name might therefore be silver carbide, but it's more popularly known as silver acetylide. So I'm going to illustrate for you the extraordinary instability of this heat by heating a small quantity which has been placed on a metal tray here. And what we're going to do now is to place a burner under it. A Bunsen burner which will, in a very short space of time, cause it to detonate. Now, when it detonates, it really does make a very loud bang indeed, and we hope you'll see the flash. And obviously, for this purpose, because this is such a very loud bang, I'm going to put on ear defenders. So here are my defenders. Obviously, safety goggles as well. And I'm going to put these on. Actually, let's put, sorry, I haven't practiced this bit, obviously, but here we are. Let's try once again. And now, that's right. So now we put the burner under. So this is a Bunsen burner, and I'm going to put it under here, and we shall listen. And as I said, this may go off in a few seconds, it may go off in a minute or two, but I think it's not going to be too long. And there it is, a small crack there. Perhaps there'll be another crack, we don't know, but you've certainly got the idea there. I'm just going to have a look. I think that was it, actually. So I think we've definitely demonstrated this reaction. If there's a tiny bit more, I may actually come back to that later. But it worked, basically. You saw a flash and you heard a bang. This is a bit of hit and miss. It depends on how the substances were prepared. But in essence, you saw a definite, very rapid reaction. Now, what I'm going to do next is to go back to this luminosity and go back to our flame which we had at the beginning. One of the things, as I said, that Edmund Davy recognized right at the very beginning was the fact that the flame from this carburet of hydrogen, as he called it, was very, very luminous. And you saw the yellow luminous flame from the gas jar. You also saw the luminous flame of complete combustion in this jar here. And of course, the very luminous flame at the beginning. And at a time when people were experimenting with ways of making light, artificial light, which had been known for burning various oils throughout the years, throughout the centuries, various vegetable oils, and in fact through burning animal oils as well, which is very sad in today's world, but whale oil was used on a very large scale for providing illumination. But attempts were made to try and find other ways, of course, without destruction to our environment and to our living species. And so acetylene was seen as a very, very good use of a very good material for making flames, as I just showed you. And in fact, those cycle lamps there, which I showed you, had actually predecessors. And what I've got here is a miner's lamp. I'm not going to be actually showing you the flame, but I'm going to show you how it's made. And it's made like this. We have a bottom, which we have here, which is filled with calcium carbide. So calcium carbide is placed in there. There is then a small water reservoir here, and if we turn the tap, you'll be able to see water dripping. There you see, that's water dripping, and that can be very carefully controlled to give just the right level of water dripping. I've now closed it off, and as the water drips, so we have a carefully controlled stream of acetylene. And it's that stream of acetylene which is then fed into our orifice through very carefully designed nozzles, which have to be regularly cleaned because they foul up with carbon. And that then is these miner's safety lamps, by the way. They were used for lamps for illuminating because they weren't safe because they had a flame in them. They were used especially in mines where metal ores were being extracted, where there was no danger of flammable gases. So let's continue our journey on the luminosity and on the combustion of acetylene with an industrial application. And such an industrial application is in oxyacetylene welding. Now, not only is the flame from the acetylene very, very, very luminous, but it's also exceedingly hot. And that was already noted some time ago. That was already noted by chemists and by scientists in general. And it was exploited, this extreme heat of oxygen was exploited in the year 1903, when for the first time people were able to store gases under pressure, pressurized gases. We're looking at the turn of the 19th to the 20th centuries, and therefore that means a large volume of such a gas could be stored and used for purposes for the benefit of others. And I'm now going to show you the oxyacetylene welding equipment, which I've set up here. And behind me, out of your sight, is an oxygen cylinder and an cylinder of acetylene. Incidentally, acetylene is so dangerous when it's compressed that you cannot store compressed acetylene. It's liable to detonate. So the way it's stored safely under pressure is by dissolving it in acetone. So my cylinder of compressed acetylene actually contains a huge amount of it, it's filled to the brim with acetone, and acetylene is dissolved under pressure. I'm now going to ignite my burners here, and then I'm going to show you some remarkable effects of this very, very hot flame. However, before whoopsie-daisy, just as you see, careless, I have spoken, but that's of no concern, these things happen. I'm going to now focus onto the equipment which I have on my large retort stand here. In my retort stand here, I have got 3 items. Now, one of them you see is a plate of steel, one of them is a glass test tube, and here is a stick of chalk. And I'm going to show you, in turn, one at a time, what happens when each of these are subjected to the very high temperature of an oxyacetylene flame. Now, the way we put it, if you don't mind, I'm going to start off, obviously, by taking some safety precautions. I'm just going to move my apparatus around a little bit as well, just out of the way here, and we can put our flask over there, in order to make space, or to make some space for the equipment to do with the welding. So if you don't mind, we'll just put things out of the way there. I'm just going to put these here, and then I'm going to move some more interesting equipment, which I'm going to be demonstrating in just a second here. So, we've now set ourselves up for a short demonstration on oxyacetylene welding. Now, first of all, once again, safety spectacles are very useful in this situation. And then we can just move away our plate there. And at the same time, maybe I'll just place a tiny bit of acetylene on there if there's a bit left in here. Actually, not enough, so we won't bother with that. And now what we'll do is we'll take this here, and I'm going to show you how to light the oxyacetylene flame. So we start off by just opening very gently the red one, which is acetylene, and then putting it, very briefly, putting it into a, so there we are. So there's a very, very tiny acetylene flame. Now that's acetylene burning in air, and you will see it has a yellow flame with a huge amount of soot coming off. Obviously, this is incomplete combustion once again, and we can increase the size of the flame gradually. That's what we call laminar flow there, so it's a relatively low speed of issue of the acetylene, but the amount of smoke is seriously large. But that doesn't matter. We have a large ventilated room. So as we increase the pressure of the acetylene, so you notice the luminosity starts to increase, and you notice this area here we have turbulence. So the flame is turbulent, it's laminar up to there. But now what we do, we start adding oxygen. And this is where we start to increase the temperature of the flame, because we increase the proportion of complete combustion. So now you see we have a very, very luminous flame. It's very luminous in the middle now. And now you see the luminosity even greater still. But as we continue to increase oxygen, the luminous turns to a blue color. And for those of you who are familiar with Bunsen burners, we now have a miniature Bunsen burner flame with a cone of unburnt acetylene right in the middle there, and that's the bright blue, and the cone of burnt acetylene obviously around. So this is like a miniature, a Bunsen burner in miniature. Of course, in a Bunsen burner we have oxygen, we have air and methane, but here we have what? So I'm looking for my gauntlets. Just found my gauntlet. Obviously, if I'm going to making things get very hot, then clearly it makes sense to have some sort of protection from heat from my hands. So if you don't mind, we'll just put on the glove here, and then we shall show you some simple experiments. Now, the first experiment I wanted to show you is how the flame affects glass. What I've got here is a glass which is Pyrex glass. It's resistant to high temperatures, and nevertheless, this temperature we have here is about 3,000, just over 3,000 degrees centigrade. That will certainly be enough to melt glass. So if I now start heating this up, you'll notice that there's a bright orange color. Now that bright orange color is due to the sodium content. This glass is primarily a lot of sodium carbonates used in the manufacture, and there's silicates as well. So that's the bright orange color. However, and you see already, it's beginning to be deformed. This is what we call plastic deformation. The glass is now, and gradually, the neck is beginning to get lower, thinner and thinner. And at a certain point, which I'm going to try and judge carefully, the bottom of the glass should fall away and fall maybe a few centimeters or a little way. Hopefully you'll be able to see very thin a glass thread as it falls away. So I'm going to very carefully, I'm taking great care to make sure this doesn't happen too rapidly. And you can see it's gradually sinking, gradually falling away there, and there. And I have to be patient, not to overdo it, because otherwise it'll just fall to the floor, which I'm trying to avoid. I'm trying to get it to fall by a sort of 15 centimeters, 30 centimeters. There we are. There it is. You can see we have plastic flow now. This is plastic flow, just a tiny bit, but I think you all see. Oh, dearie me. Did you see that? It went right down. It went to the ground. I overcooked it, but there it is broken. However, I have got a sample that I made earlier because this is exceptionally difficult, but there you see a sample which I made earlier, which I managed to get it exactly at the right level. So these experiments are not easy, they require a lot of practice, and as you see, I didn't quite get it, but I certainly showed you the effect there of a high temperature on a heat-proof glass test tube, up to a certain level heat-proof. Now, I have here, in my next experiment, if you don't mind, what I'll do is, I will just put I have a special stand here, which can safely hold that. I will just disconnect my glass apparatus now. So my tube I'm taking off, and I'm going to show you an experiment with a piece of chalk. Now, I have here a piece of chalk here, which is essentially made of calcium carbonate. And the interesting thing about this is that this, when it's heated, will do something very, very unusual. It decomposes to give calcium oxide and carbon dioxide, but the interesting thing about it is as it does so, it gives off an extraordinarily bright light. And there you see, I am now in this light, and this is the sort of light that was used in theatre productions. Today we have the well-known expression, in the limelight. Now, as you can see, I am now literally in the limelight, and I'm being illuminated, and I hope you could see very brightly indeed, a remarkable phenomenon indeed, which I have no idea how to explain, but by gum, this is very, very bright indeed. And this, of course, was used in theatres by heating large lumps of light to a very high temperature, and so there we have another very interesting effect of high temperatures, this time causing a chemical reaction once again. It's the thermal decomposition of calcium carbonate into calcium oxide and carbon dioxide, and this gives off light energy. Now, I'm now going to move on to higher temperature effects, and for that purpose, I must now change my safety goggles. I'm actually going to show you how we can use the extraordinarily high temperature of the oxyacetylene flame to melt iron and indeed to weld iron. So I have a steel sheet here. I have a sheet of steel. This is a relatively thin sheet of steel, and I'm going to heat it from behind using my oxyacetylene flame. Now, because the temperatures which are generated here are very high indeed, and because I'll be needing to control the flame carefully, I've now put on a special pair of welding goggles. These welding goggles, as you can see, have dark lenses of them, and they enable me to carefully control the effect. So what I'm going to try and do in this first experiment is simply to burn a hole through the steel sheet. Now, I'm going to heat it approximately in the middle, and as I start heating it, I hope you'll see it will start to glow orange. And as it starts to glow orange, and you see I've already burnt the hole. There it is. And the hole has come through very quickly indeed. Now those are sparks. The sparks which are coming off are sparks of burning iron, in fact. It's iron burning in air, these shower of sparks, to make triferric tetroxide Fe3O4, tiny little sparkles. You see, incidentally, the ring of colours, that ring of colours around there represents the different layers of iron oxide, and this is very important to recognise these colours. They're used in metallurgy to assess the element of heat treatment. In heat treatments of steel, we look at the colours of oxide layers, believe it or not. And now for my final experiment with oxyacetylene welding, I thought it would be appropriate to actually weld something together. Now, to weld something together, obviously we use steel is the best. Steel has a melting point of around 1550 degrees centigrade. We've got a temperature there of roughly 3000, so we're certainly within range. And I thought it would be, rather than welding something conventional, I've got something here which I thought we could make practical use of. Now, this is a selection of coins. This is a selection of coins, 2p and 1p pieces. And if I use my magnet, you'd think they're made of copper, but not always. If I put my magnet there, nothing happens, you see. No reaction, doesn't pick up. Well, it's obviously if it's a copper coin, but then if I put here, you see that copper coin is clearly not copper. That's mainly steel. And if we carry on working our way around, you see this one also made of steel. Carry on here, another one clearly made of steel. Then try yet another one. That's one made of copper. Very straightforward. They appear to be the same, but a magnet in a very short space of time tells us the difference. Now, I've taken off enough coins for the demonstration I wanted to show you, because what I thought I would do now is I would weld these coins together. Since we have recognized that they are all made of steel, I'm going to weld them together and make a very unusual piece of, a very unusual coin. If you add together 2, 4, 6, it'll be a 7p coin. Now, that will be a very unusual coin, as I'm sure you recognize. And what I intend to do is to weld the three of them together. And then, while they're very hot, I'm going to pick them up with my tweezers, throw them into a glass of a beaker full of water, and then hopefully we'll have a 7p coin. Once again, this is a very difficult process. And in order to do this, we have to use a welding rod. Now, this welding rod here, you'll see, it's got a copper colour on it, but of course, it is steel, in fact, and there you are, we can hold it with our magnet. And the reason why, of course, it's coated with copper is to protect it from rusting. Iron is very, very prone to rusting in a moist atmosphere, and therefore we need to protect it. So I am now going to put my gauntlets on. Now, this may take a couple of minutes. This is not an easy procedure. I have to take great care not to melt the coins too much, and it requires considerable hand-eye coordination. So, as I said, you'll have to bear with me, but I think if we get a good result, then it should be something to be very pleased with. So I'm going to now start heating my 2p coins. The trick is you have to heat them both evenly, because if you don't heat them evenly, then basically the iron, the steel filling rod will not go in exactly. So I'm moving my flame and seeing whether I can get them sufficiently molten. The process is known as puddling. Once I see a puddle of molten steel, then I'll know that I'm ready to. So it's taking a little while. This is not easy. You may see some sparks. Sometimes you may get a bang, by the way. You must not be too put off by this. See, at the moment I'm having to melt the bottom coin because that one is the one that's... So we have to get the steel. In order to make a weld, you have to actually melt the surface of the metal. And if you hear a slight whistling sound, that means I've got a little bit too close. So I'm still going to, so it's still, we haven't quite yet, we haven't got it. I think we have a successful weld. As I said, this is not easy at all. You see the spark, sometimes you hear a little bang and then explosion, but that's all stuff which is well within. There we are. So let's have a look. Just have a quick look there. Hopefully we've got that. I'm just going to have to remove my... I think we've got a result there. I can't be sure. So we now move on to the next one. Once again, one has to distribute the heat evenly. You have to get them both to have a little puddle of molten steel on the surface of the coin. Otherwise, you'll never join it. Now, coin has just slipped a little bit there, so I'm not sure whether we're going to succeed, as I say. Difficulty. Maybe we've got a result. Perhaps we've got a result. That one slipped a little bit. I'm just going to have a look. May have just about got a result. Let me try once again. I think I've got a result, but I like to it's not brilliant. But you know, it's, as I said, the conditions here, and without doing this on an everyday basis, then it really is quite tricky. But I think we have something. I think the whole lot is moving. think the whole lot is moving. Yes, let's just burn that off. Now, the 1p coin I think has become detached. No, it hasn't. Brilliant. So we're still there. Now let's try and do the 1p coin. So let's try and do the 1p coin. Once again, we have to get the 2p coin melted first. It's got a higher thermal capacity. Once that one's got a bit of a puddle, then we move on to the 1p coin. And there it is. It's getting slowly a little bit more. A little bit more. Let's see. Right, so there we are. Let's see. So let's see whether we've been successful. First thing is we turn off our welding gear. So we turn off first of all the oxygen and then we supply the oxygen. So that's always the important correct order. Having turned them off, we now place this here. And now the big moment, have we succeeded? So we try and pick up our coin, whether they've all succeeded or not. Amazing. So there it is. A real 7p coin welded together in front of your eyes. Let's now cool it down. We drop it into our large beaker of water here. We can watch carefully. And there. And so now, very quickly, we can now take our gauntlets off because this will be quite cool to the touch. And let's see. Not brilliant. It's by no means brilliant welding, but it's illustrated the principle. So you see, the best glue for steel is steel itself. And that is achieved in this splendid process of oxyacetylene welding, which is a chemical welding technique, a very difficult technique, but nevertheless, as you see, it affords excellent results. Now I'm going to finish off now. One must again demonstrate the explosive properties of acetylene. These experiments, I have to repeat, are not at all easy, and they involve all sorts of risks. However, there is a sort of a nice experiment which I'm going to try and show in front of you here. I'm going to just move around my apparatus a little bit for this purpose. Now, first of all, I'm going to move my bricks. Obviously, we had to have, this is very, very hot indeed. Obviously, not that hot, otherwise I wouldn't be holding it with my gauntlets. So there we've moved our metal plate. We should certainly keep our 7p coin in view because that's well worth keeping. And here we have our final piece of apparatus here. Now this is nothing spectacular, but because once again, as I say, there is a considerable amount of danger in these experiments. And what we're going to do is to generate a small quantity of acetylene in there, and it will mix with air. We only want a tiny amount. And when that tiny amount of acetylene has started to be produced, I'm going to plug the hole here with this cloth, you see. Now this cloth, what I'm then going to do is to apply a lighted flame there, and hopefully the cloth will just pop out. And that will be the final demonstration. There's no bang involved, it'll just be a little pop with a little bit of a flame. So fingers crossed this will be successful. So, in order to do this, we have to have our tin here. There is some water already placed in there, and I'm going to now place in, I have to move fairly quickly by the way, so if you don't mind, I'm going to get myself a lighted splint. I have some splints around, you must excuse me. I think the only one I got is this. Too bad, we shall use this and we shall make use of it. And I'm going to just have my flame there, just checking everything. Always double check. There's nothing that can happen which is unexpected or dangerous. This is still very hot, by the way, this flame here. So I'm going to apply a lighted splint there once once I've added my 2 pieces of. So this will be the procedure. I have some calcium carbide in my tin here. I'm going to place 2 pieces of calcium carbide in there. I shall immediately plug the hole with my cloth, and then I shall apply a light to the tube coming out of the Buckner flask which I have here. I've got some matches here just in case the splint doesn't manage to carry the flame. So, taking a couple of pieces here, couple of pieces of, let me just pick up 2 pieces immediately, get the right number. We don't want to do, there, we have 2 pieces here. We have to be prepared for rapid action. Before I do that, let's just, safety precautions. First one, never knows. As I said, these air mixtures are very, very, they burn with extreme rapidity. So 2 pieces, you'll notice immediately it's starting to froth, and immediately I will put the plug of our cleaning plate there, plug this in now, and then I shall apply very rapidly a flame. Let's just light it with a match, and hopefully the thing will come popping out. So just get our flame. Whoops, that one wasn't so good. Try once again. Here. And now, fingers crossed for a successful propulsion of the cotton cloth. And there you see. So, the experiment was very successful. The cloth has flown out of the flask. Thank you very, very much indeed for watching. Very, very best wishes.